So it should not.
First, and then share that. Just stop screen sharing and start with the chat feed.
Oh, so I'll stop share. Where is that? Oh, yeah. Stop the share.
Now I'm sharing.
Right here.
All right, we're all ready to get started with the third talk. That's by James Bartusek on the indistinguishability obfuscation of null quantum circuits and applications.
Okay, thank you. So yeah, I'm going to be talking about this indistinguishability obfuscation of null quantum circuits and applications, and this is joint work with Giulio Malavolta. Okay, so first I'm going to share some background on the notion of classical indistinguishability obfuscation, some of which we saw in the last talk. But so an obfuscator is just a compiler that takes as input a computer program, and for now let's think of this computer program as some classical program, and obfuscates it. So it's a compiler that you apply it to the program, and out comes an obfuscated program. And the point of an obfuscator is to scramble the implementation details of this program while maintaining its functionality. Okay, so you basically want to hide everything about how the program is implemented, except for the actual functionality of the program. And for this particular notion of indistinguishability obfuscation, which I'll be discussing today, the security property that we hope for is that for any two functionally equivalent programs, P1 and P2, their obfuscations are computationally indistinguishable. And so maybe at first glance, it doesn't seem like this notion is very powerful, but it turns out to be extremely powerful, at least in the world of classical cryptography. And a few years ago, it's actually been dubbed the central hub of cryptography for all its many applications. And these include things like fully homomorphic encryption, multi-party non-interactive key exchange, so functional encryption, so strong, like fine-grained notions of public key encryption. And it's also been shown to be quite useful in the quantum setting as well. For example, public key quantum money, along with all the applications we saw constructed in the last talk. Okay, so again, over the past about 10 years now, there's been a huge amount of work studying the many various applications of this notion of indistinguishability obfuscation. And at the same time, the last decade has seen also a huge amount of work on constructing this notion. Okay, so starting again about 10 years ago, we had the first candidate constructions of obfuscation for classical circuits. And now today, after again, like a decade of work, we have a construction of obfuscation from well-understood assumptions. Unfortunately, this includes also an assumption on bilinear maps, which is not post-quantum secure. So we also have another line of work that's still actively ongoing that is constructing candidates for post-quantum indistinguishability obfuscation. So both on the application side and the construction side, the last decade has seen a huge amount of work going into this notion of indistinguishability obfuscation. Okay, so this talk today is going to be about a natural quantum analog of obfuscation. So, what if our computer program P is not classical, but what if it's a quantum program? So, for example, maybe it's just a description of some quantum circuit, and we want to apply a compiler to that circuit to obfuscate it, to encrypt everything about the circuit except for its functionality. Okay, and so this notion in the quantum setting has been much less well studied. I'll mention a few works that have dealt with it. So, a few years ago, this work of Alogic and Pfefferman basically gave a bunch of different definitions of obfuscation in the quantum setting. And more recently, a couple of works have shown that some of these are impossible to achieve, actually extending similar results in the classical setting. But on the application side, is this notion of like quantum obfuscation, could it also be seen as a central hub of quantum cryptography? So this question is much less clear. There's not a lot of work studying, applications of specifically obfuscations of quantum circuits and what that might be useful for, right? So also this one application I know of is this work of Alogic and Pfefferman also showed that quantum IO implies this notion of witness encryption for QMA. And this is actually a primitive that I'll be discussing later in the talk. But I'm not really aware of other works that have really studied applications of specifically quantum obfuscation, beyond just like it being interesting in its own right. And then also, so what about constructions? Again, there's a few works that have studied this, but not many. So a couple of works have studied, small classes of quantum circuits or, quantum functionalities that can be perfectly obfuscated, meaning that there's like compilers that kind of, output an obfuscation that's kind of perfectly secure for these limited circuit classes. And so this is good, but, if we're going to hope to obfuscate all polynomial sized quantum circuits, we're not going to be able to do this perfectly. We're going to have to rely on computational assumptions. So these kind of approaches are not going to easily extend. And then this work of Broadbent and Cosme also showed that, well, if you have any quantum circuit that consists of only Clifford gates plus a very small number of non-Clifford gates, so actually logarithmically many, then you can obfuscate this circuit based on the security of classical IO. And so actually Clifford circuits is a class of circuits that can be perfectly obfuscated. And so if you kind of make them a little bit more complicated, they show that you can actually computationally obfuscate this class of circuits, okay? But this is pretty much, as far as I'm aware, this is pretty much it prior to our work. And so I do just want to highlight one question that's still open today. Is it even possible to realize indistinguishability obfuscation for all polynomial sized quantum circuits? Okay, so this remains open. And this is in contrast to the classical setting, because we still don't even have any candidate constructions. We have no like plausible constructions of this that we can even begin to analyze. So this is kind of like living in a world of like pre-2013 in classical cryptography in terms of obfuscation. Okay, so I think this is a pretty cool open problem. We still don't even know how to, any plausible candidates for solving this general question. So, given this background, I can talk about our work, and our work addresses this notion of quantum obfuscation from both the construction side and the application side. So I'll first tell you about what our construction is. So assuming the quantum hardness of learning with errors, which is a pretty standard post-quantum security assumption, along with this notion of virtual black box obfuscation for classical circuits, and I'll return to discussing this in a little bit. What we can show is that there exists an obfuscator that takes as input a quantum circuit, and outputs an obfuscated quantum circuit with the following properties. So correctness, meaning that the obfuscated circuit roughly preserves the functionality of Q just up to negligible errors. And our security property is that for any pair of null quantum circuits, Q1 and Q2, so these are quantum circuits that output 0 with overwhelming probability on every input, okay? Then we can show that the obfuscations of these two circuits are computationally indistinguishable. And so this is this notion of null IO has actually been studied in the classical setting, classical null IO, and essentially this is a quantum analog of that notion. Okay, and so before moving on, actually to discuss applications of this, because it actually, if you're not familiar with the notion of classical null I/O, it's probably unclear like why this isn't even an interesting class of circuits to obfuscate. I do want to return to this assumption for a second. So as also mentioned in the previous talk, this notion of VBB, virtual black box obfuscation for classical circuits, has been shown to be in general impossible to achieve. Okay, and it's even impossible to achieve, using quantum information as well. But that doesn't necessarily mean that this whole construction is meaningless, because what you could do is you could say, okay, we actually need this notion of VBB to get our security proof to go through, but you could heuristically instantiate this obfuscation with an obfuscation that just satisfies at least post-quantum indistinguishability obfuscation. So it's kind of like our proof requires this idealized model to go through, but you can instantiate this obfuscation with an IO of which we have many plausible candidates for. Similar, granted it's a little bit stronger, but it's similar to what people do with the random oracle model when you instantiate that with a hash function. And then I also wanted to mention in the paper, we show how to replace this particular assumption with what we call dual mode classical verification of quantum computation. This is a notion that we define, and I won't go into the details of that, but I will say also we only have heuristic constructions of this. So maybe the takeaway from this construction is that what we give is a heuristic or a candidate construction of IO for a large class of quantum circuits, namely all null circuits. Okay. Good, so now I'll move on to discuss applications. Again, because it's probably not very clear that quantum null I/O even has applications. So the first thing we show is that our notion of quantum null I/O actually is still powerful enough to imply this notion of witness encryption for QMA that I mentioned earlier in the talk. And our witness encryption scheme also even has a classical ciphertext. And given this primitive, we actually show it has actually a huge number of applications. So from a non-interactive zero knowledge argument for QMA, kind of a two-message version of this primitive without setup. We also give the first attribute-based encryption scheme for quantum predicates, and a few other applications. And so I'll also mention that none of these applications on the right were known prior to our work, even making heuristic assumptions. So, going through our null I/O to witness encryption to constructions of these give kind of the first candidate constructions of all these applications. Okay. And yeah, so for the rest of this talk, I won't mention these applications all the way on the right. I'll encourage you to see the paper for why these are implied by witness encryption and how we construct them. In many cases, we also need additionally the assumption of classical I/O. But for the rest of this talk, I wanted to just first discuss witness encryption for QMA, why it's implied by quantum null I/O, and then give and then talk a little bit about how we actually construct quantum null I/O. Okay, so so first, what is witness encryption for QMA? It's a straightforward, analog of this notion that's been studied in the classical setting of witness encryption for NP. Okay, so here we just fix any language, QMA language L, and the encryption scheme takes as input some message M and some instance X, and output some ciphertext based on, computed based on M and X. And so we have a correctness and a security property. For correctness, we say that if X is an L, so if X is a yes instance in this QMA language, then any witness psi for X can be used to decrypt the ciphertext and learn M. Okay, so there's some procedure that takes as input the witness and the ciphertext and returns to you the message M. So that's correctness. Security requires that if X is a no instance, then no efficient adversary can recover M from the ciphertext. Okay, so as long as your adversary is computationally bounded, there's nothing they can do to recover the message from this ciphertext. Okay, and so this is actually the notion once you have this notion of witness encryption for QMA, we show how to construct NISICs for QMA and attribute-based encryption, and the various other applications that I showed on the last slide. So now I want to describe to you how you can actually build a witness encryption scheme from null IO. And there's it's been known in the classical setting that classical null IO implies witness encryption for NP. This is just a straightforward analog of that. So to encrypt a message M under an instance X, we'll define, let's define this circuit QMX to be a quantum circuit that takes as input some quantum input psi, and then outputs the message M if and only if psi is a valid witness for X. So basically the circuit is just running the QMA verification procedure. If it accepts, it outputs M. If it rejects, it just outputs nothing. Okay. And then our ciphertext for this witness encryption scheme is simply going to be an obfuscation of this quantum circuit. Okay. And so why is this a good witness encryption scheme? Well, by the correctness of our obfuscation, this obfuscation is maintains the functionality of Q. So if you have a witness, so if X is a yes instance and you have a witness psi, you can just plug this into the obfuscation to learn M. So on the other hand, and this is where the security of null IO comes in. If X is a no instance, note that QMX is actually a null circuit. There's actually no, just because X is a no instance, there's no quantum input that makes this circuit accept. So we can apply the security of null IO to replace this circuit that we obfuscate with a circuit that has nothing to do with M, thus showing that we can hide M. So this maybe also gives you a sense of why null IO can be interesting in cryptographic contexts. Okay, good. So this is just the basically the implication of null IO to witness encryption. And in the last few minutes, I want to discuss basically how we construct our notion of quantum null IO. Okay, so first I'll describe the two tools we use to construct this. The first one is kind of a mouthful, but it's just a classical verification of quantum computation, or a CVQC protocol, that is 2 messages and satisfies blindness. Okay, so what is such a protocol? Well, it's just an interaction between a quantum prover, okay, P, that has some input X, and a classical verifier V that has some input Q. So here Q is a quantum circuit. The classical verifier would like to compute this circuit on some input, but they're classical, they can't do it, so they're going to need to use the prover to help them with this. So this protocol consists of, the verifier will first run some gen algorithm on Q to produce some public parameters, which they'll send to the prover. The prover will, take their input X and essentially evaluate Q on X. But while doing this, they kind of evaluate it along with a proof that they evaluated it correctly. So they'll send that proof back to the verifier. The verifier will be able to essentially learn the output Y and be convinced of the correctness of Y. Okay. So, from such a protocol, we'll need 2 properties. So one is just this property of blindness. And this actually ensures that the prover can't learn anything about Q by interacting in this protocol. So in other words, these public parameters hide the description of the circuit Q from the prover. And then we just need the standard notion of soundness, which is basically just saying that the prover can't convince the verifier to output a false output. Okay. And so to construct such a 2-message protocol, we basically combine some recent work in this area. So, the work of Mahadev in 2018 was the first work to study and give a construction of CVQC, classical verification. And then there are some follow-up works that showed how to basically, compress the interaction of this protocol actually all the way down to 2 messages, at least in the random oracle model. And so we take this protocol and then we essentially just combine it. We run the entire thing under a quantum fully holomorphic encryption scheme in order to make it blind. Okay. So this is how we can get this 2-message blind CVQC protocol. So that's one tool. And the other tool we use is just this, like I mentioned before, is a obfuscation, but for classical circuits. Again, something that we have many candidates for. Okay. Okay, so given these 2 tools, our construction of null IO is pretty simple. So here's the construction. If you want to obfuscate a circuit Q, basically what you're going to do is first run the verifier's gen algorithm on Q to produce some public parameters with respect to Q. And then you're just going to output a classical obfuscation of the verifier's output function. Okay, and so this is like, these two components make up our null IO scheme. So the public parameters and a classical obfuscation of the verifier's output function. And so this, this output function has to have Q hard coded along with any like secret randomness that the verifier used to generate the public parameters. Okay, and so how do we evaluate this scheme? So let's say I'm a quantum evaluator. I want to learn this program on some input X. I can just run the prover's algorithm to basically compute X kind of blindly, along with a proof that I did it correctly. I'll just plug that proof into the classical obfuscation and thus learn the output Y. And so basically, at a high level, this obfuscation scheme is essentially saying, well, I'm going to allow the quantum evaluator to do the evaluation, but under an FHE scheme, essentially. So they can't learn what they're evaluating, but they must produce a proof that they're evaluating it properly. And if they do that, we can plug that into a classical obfuscation and allow them to learn the output. Okay. So good. This is the construction, and now I can say a few words about why this is secure. So for security, we'll just fix, so first let's say that we're dealing with some null circuit Q. The first thing we can do is say that this classical oracle, so V out, the first thing we can do is just replace this oracle with an oracle that always outputs 0 on all inputs. And the reason is that we can show that any adversary that distinguishes this oracle from the all zeros oracle, even if they can query the oracle in superposition, that adversary can be used to break the soundness of the CVQC scheme, essentially by extracting a cheating proof from this adversary. Okay. And once we do that, we're almost done. Now we just have to note that these public parameters actually hide Q due to the blindness of the CVQC scheme. So essentially what we've done is shown that both of these components of the obfuscation essentially hide Q from the evaluator. And this is the high level description of our security proof. Okay. All right, so this is the construction, and I just want to conclude by mentioning some open questions, and I think this work does give a number of interesting open questions. So first of all, I've just been talking about null IO this whole time, right? Obfuscating circuits that always output 0, and the security proof I just presented only works for null circuits, but why is that? So you could try to apply our same template to obfuscate any circuit, say with classical output, but this actually runs into an issue. Okay, so if you try to obfuscate circuits beyond null circuits, what you realize is that what we would require is a stronger property from the underlying CVQC scheme. We don't need just soundness and blindness. We actually need these notions of reusable soundness and reusable blindness, meaning that a prover who even is allowed to query the verification algorithm multiple times over and over again can still not break soundness or blindness. Okay, and so we actually show that like known CVQC schemes are not reusably sound or blind. So we actually show explicit attacks on these schemes. And so this leads to a pretty clean open question. So whether we can actually construct such CVQC schemes with this stronger security property, and then whether that then allows us to obtain obfuscation for larger classes of quantum circuits. Okay. And then the other open question is, like I mentioned, all of our results are assuming virtual black box obfuscation of quantum circuits. So essentially, we need to assume, our results are essentially with respect to a classical oracle, right? And so, like we saw in the last talk, it's quite interesting to try to remove this oracle assumption or remove this heuristic and actually get provable security just based on indistinguishability obfuscation. And so this is an open question. Indeed, either null IO or any of the implications that we show, from witness encryption to NISX to ABE, these are all open to construct without oracles. So just from IO plus LWE. And so thanks for listening.
Thanks a lot, James. Any questions?
Great talk. I just wanted to understand like how this quantum IO is different from quantum compiling.
Quantum compiling?
Yeah, so given any circuits, you just compile it so that it is very like in shorter, like very limited number of gates are there, and yeah.
Yeah, I mean, well, it's asking for like a strong security property, basically.
Okay.
That like it is a compiler, but it's a compiler that that provably basically hides all information about the original implementation of the circuit.
But in compiling also, like if I give you a compiled circuit, you won't be able to go back. Like multiple circuits can have the same compiled circuit, right?
So yeah, you might not be able to go fully back to the original circuit, but maybe you'll still be able to learn some information about the original circuit. And IO is saying you can't learn anything at all except for just literally the functionality.
Yeah. Thank you.
Thanks for the talk. What do you think about the feasibility of constructing quantum null IO in the standard model? Do you see any barriers to doing that?
I mean, I don't see any barriers. We try like basically what we need from our security proof is like extractability. So we need to extract a cheating proof for the underlying CVQC scheme, and we kind of only knew how to do that by treating this obfuscation as an oracle. I mean, we also tried some like various IO tricks, but it's, we weren't able to prove it, but I don't see any inherent barriers to getting it just in the standard model. Yeah.
Okay, thanks.
Have you thought about extending broadband and Cosmos construction for Clifford plus low T gates to arbitrary number of T gates using like magic states, for example?
No, I haven't thought about that. Extending that construction to more T gates?
Yeah.
Yeah, I haven't thought about that. Yeah. Okay, the online question is, can you again explain why the security of null IO follows from soundness of CVQC? Right, so there, right, so essentially, if Q is a null circuit, coming up with any proof that causes the verifier to accept is considered a cheating proof. And so, the security of CVQC stipulates that no, at least polynomially bounded prover can come up with such a proof. And so that's essentially why we can replace this oracle with the all zeros oracle, because if any evaluator can distinguish this oracle from the all zeros oracle, then we can extract from that evaluator a proof that causes the oracle to output 1, which causes the verifier to output 1, which means that proof is a cheating proof for CVQC.